Good afternoon, and welcome to the 12th Annual Benjamin and Ann Pinkel Lecture. I'm Professor John Truswell. I'm the Director of the Institute for Research in Cognitive Science here at Penn. This is, as I just said, the 12th in the series of Pinkel Lectures. And the Pinkel Endowed Lecture Series was established 12 years ago through a generous gift from Sheila Pinkel on behalf of the estate of her parents, Benjamin and Ann Pinkel. The series serves as a memorial tribute to their lives. Benjamin Pinkel received a bachelor's degree in electrical engineering here at Penn in 1930. And throughout his life, he was actively interested in the philosophy of the mind and published a monograph in 1992 on the subject entitled Consciousness, Matter, and Energy, the Emergence of Mind in Nature. In fact, we have a copy right here, which will be a gift to our speaker. The objective of the book was, and I quote, a re-examination of the mind-body problem in light of new scientific information. The lecture series is intended to advance the discussion and rigorous study of the deep questions which engaged Dr. Pinkel's investigations. And over the past 12 years, the series has brought some of the most interesting minds in the field of cognitive science as it pertains to thought, learning, and consciousness. These include Daniel Dennett, Liz Spelke, Martin Nowak, Stan DeHaan, Jeff Hinton, Ray Jackendoff, Colin Kemmerer, Alyssa Newport, Christoph Koch, Alvaro Pascal Leon, and Alvaro was last year. It's a great pleasure to add to this list, this esteemed list, Dr. Patricia Kuhl, who will be speaking about cracking the speech code, language, and the infant brain. Now, Dr. Kuhl is the Bezos Family Foundation Endowed Chair for Early Childhood Learning at the University of Washington. She's co-director of the Institute for Learning and Brain Sciences and director of the University of Washington's NSF Science of Learning Center, and she's also professor of speech and hearing sciences. She's known internationally for her work on early language development and its neural underpinnings. She's perhaps best known for her research demonstrating that early exposure to a language greatly alters how infants perceive and process speech. Dr. Kuhl's many years of research have aptly demonstrated, and I quote here from one of her papers, infants are born citizens of the world with regard to language. They can distinguish sounds from languages around the world, even if they've never heard them before. By the end of the first year of life, however, they become language specialists, and the ability to attend to sounds from foreign languages greatly diminishes as their native language abilities significantly increase. This is truly groundbreaking work that has shaped a generation of speech perception researchers, cognitive scientists, and cognitive neuroscientists. And for this, she has been internationally recognized in many ways. She's a member of the American Academy of Arts and Sciences, the Rodin Academy, the Norwegian Academy of Sciences and Letters. She was awarded the Silver Medal of the Acoustical Society of America in 1997, and in 2005, the Kenneth Craik Research Award from Cambridge University. She's a fellow of the American Association for the Advancement of Science, the Acoustical Society of America, and the American Psychological Society. And in 2008, in Paris, Dr. Kuhl was awarded the gold medal for the acoustics branch of the American Institute of Physics. It's truly an honor to have Dr. Kuhl here as the 12th Pinkel Lecturer, so please give a warm welcome to Dr. Kuhl.
I'm very excited to be here today and very interested to learn more about Professor Pinkel. I had no idea that he was prescient in terms of telling us how important study of the mind was going to be. It's a great pleasure to be here and see all my old colleagues and talk about something I really love, and that is the science of learning with regard to language and the human brain. The human's ability for language has stunned many great scientists for centuries, and I think that the theories are moving along. A lot has been discovered since we actually started studying babies in the early 70s. Early theorists had not. What we've uncovered in these studies is quite stunning and leads us to sort of revise the model by which we imagine children are going about their task every day as they learn a language or two or three. We've always been interested in the extent to which language relies on special machinery and relies on special psychological processes. And that, too, is under revision as we look at new experiments that involve, from the very beginning, infants' social skills and cognitive skills. So we'll have a lot to say about that today. It's very interesting that the infant data are playing a very significant role in the debate about language. So I'm going to start today by showing what I think is a very interesting and mysterious process, what biologists will call a critical period in development. And language is one of the quintessential examples when biologists talk to people and want to give an example from human development rather than animals. They point to language and say, there is a critical period with regard to learning. If you find your age on the bottom of this curve and look at your skill, this cartoon sort of illustrates what the phenomenon is all about. As opposed to many other things in the psychological literature, adults are not better at the acquisition of a second language. They're actually worse and substantially worse. And this curve, which actually is a cartoon kind of representing the data shown in a paper by Johnson and Newport some time ago, summarizes a lot of literature having to do with syntactic performance in a second language and phonological performance in a second language. And what it illustrates is that between 0 and 7, the kids are brilliant, regardless of how many languages you put in front of them that they're exposed to. They will acquire those languages with great skill. And beyond the age of about 7, there's a systematic decline. Decline can be seen at 8 to 10 years, at 11 to 15 years, and 17 to 39, I guess that's most of us in this room, maybe all of us in this room, you kind of drop off the map. It isn't as though you can't learn a second language, but you do it differently, and it is not as automatic, and particularly with regard to the subtleties of syntax and phonology, with the production and perception of speech in particular, you never become the expert that you would have become had you been exposed in the first 7 years. Now, in addition to this being a fairly depressing curve to start out a talk with regard to demonstrating your lack of skill, it provides a really fundamental puzzle that a lot of people have grappled with. No one really disputes this curve, and we know that the curve is made up of little curves. There are curves in here that you could draw for phonological learning, for word learning, and for syntactic learning, where the infants and children seem to specialize in that aspect of language learning. But the broad curve is not disputed. What is under great debate is what causes it. What's it about? Lenneberg had a hypothesis early on that it had to do with the brain and the development of the corpus callosum, and that everything changed with regard to the brain once the corpus callosum was in place, which happens at about the age of 5. But that's no longer what we consider to be the most interesting hypothesis. We're working on what's going on in the infant brain at that period in development. We're hypothesizing that it's learning itself that causes the failure to learn later, that the neural architecture, the composition of the neural networks that develop as you're exposed to the signals coming from a particular language, its auditory patterns, its statistical properties, builds networks that are then resistant. Your networks for Japanese simply don't fit French. So once that is established, the learning itself reduces the potential for you to learn later. So that's one of the things that we're trying to entertain. We're spending our time studying the very earliest processes. Most of what I'll tell you about today has to do with what babies are doing in the first year of life. So we're looking very early on to see what the markers are. We think that we can play out major theories with regard to language development by looking at the phonetic level, the earliest processing of sounds from different languages, and how that points the infant on a particular path. The reason for doing it is, one, we hope to learn what the magic is that kids are putting to work here that we can't do here, and potentially, if we understood the algorithms that they put to work, we might imagine being able to invent training programs that would help adults learn in the more automatic and beautiful way that kids learn. And secondly, those of us who are interested in developmental disabilities, this is where they happen. So kids who have language disorders, either stemming from autism, Fragile X, specific language impairment, all of these disorders have their origins in development. Some of them, obviously, genetic impairments. But the hope is that with early diagnostics, so I'm going to show you some examples of biomarkers that we think will be effective in diagnosing autism at about 6 months of age. So biomarkers getting in early to examine the precursors for language might allow us to treat children with developmental disabilities at a much earlier stage when the brain is so plastic, when you're in this rapid period of learning, so that we could catch them up before it became too late to do so. So in order to develop the arguments, we're going to tell you a little bit about speech, all right? So I'm going to be talking not about grammar, but about the processing of sounds that are used in language and how that occurs. What are the major problems? So we start with a little bit of physics of sound, and what you see in this graph is the posture of the mouth and the tongue when you produce two isolated vowels, and these are all phonetic transcription, ah and ah. At the bottom, you see the physics of the situation where the major components, when you listen to a vowel or any kind of sound like ah or ah, what you're doing is tracing the formant frequencies. This is a steady state version, ah, ah, and you can see the distinction is in these resonant frequencies that change very slightly between these two vowels. Now, this is a steady state situation, which is not what I'm doing right now, not what we walk around doing. We're speaking rapidly, so their steady state almost never occurs. So you can imagine the millisecond changes that your auditory system has to track in order for you to hear the difference between ba and pa or ah and e. You have to track these formant frequencies in real time. They change constantly. And we're talking about millisecond differences and small differences in frequency and small differences in amplitude and duration. So these are hard from the standpoint of physics. No computer in the world has solved the problem that human minds do very early in development. And that itself is a tremendous puzzle, given that there's a little software company just across the lake from the University of Washington in Seattle whose one of their main jobs is to crack the speech code. So Bill Gates and his team of, say, 500 or so researchers now, since they've been watching us and trying to mimic with the computers what babies are doing, they have yet to solve the problem of speech recognition by machine. So there's something that we're bringing to this task that isn't just the raw statistics of the situation that a computer could solve. So I want you to get one flavor of the problem by just listening to the variability. Listen to the variability as a number of different speakers produce the vowel ah. All right?
Ah.
Ah.
Ah. Ah.
Ah. Ah.
Ah.
Ah.
Ah.
Okay, so that's not difficult, right? There, you hear all of the variations. You can tell whether someone's young or old, male or female, but you know it's an ah. Here's the same speakers producing the vowel ah. Okay, so this is the problem that Bill Gates' computers can't solve. You and I do it at the drop of a hat, but the machine just simply can't do this yet. The only speech recognition by machine that exists at the moment are programs in which you have to isolate each word and speak very slowly. So you have to talk like this because it can't sort out, can't count the words, can't find the words, can't identify the phonemes because there's so much variability. But the kids knock this problem off at 6 months of age. So if we look at the data, these are old data. One of the first pieces of data about phonetic perception, this color is awfully hard to see, but what we have here are two syllables, ba and pa. This is a cartoon illustrating that if we take one of the critical acoustic differences, change it in small steps along a continuum, what you'll see, the infant data shown by Imus et al. In Science 1971, was that babies are really keen right here at the boundary, the acoustic boundary between two phonemes. All of a sudden at that boundary they get better at hearing small distinctions. And we demonstrated a few years later that this is a deep phylogenetic ability, right? So chinchillas, and later we demonstrated that monkeys have that same tendency to break an auditory continuum right at the place where languages put the boundary. So there's something about our inheritance, there's something about complex auditory signals, it seems to be true for mammalian hearing, that was capitalized on in the invention of a sound structure from languages. And we can see that across many different languages, babies are capable of hearing these distinctions, and animals are as well. But, of course, that's not the only problem. Hearing this distinction right here at the boundary, it's fantastic for the babies. Animal data doesn't take anything away from a baby's ability to do that. It's a great leg up on the problem when you can hear these fine distinctions and you're particularly sensitive here at the boundaries. But that's not all there is. So when Bill Gates looks at the problem with his computers, this is what he sees. Now we're going to take format 1 and format 2. If you don't know anything about the acoustics of sound, of speech sounds, a vowel like ah is like a chord on the piano. The notes compose a chord, a unified chord. The formant frequencies, F1, F2, when put together with 3 other formants, produce a vowel. But the problem is there's huge variability. So these are data taken from a number of different speakers where each symbol in here, these are phonetic symbols, each one is a different talker. You can see the huge variability and overlap in the vowels of English. So you're going E, I, A, O, U in this graph. But the problem is if you're a computer, the acoustic physical measurement itself doesn't tell you which vowel it is because the overlap is so profound, right? And this is in isolated utterances. It's not in running speech like I'm doing. So you can see why we're not all typing into, we're all still typing into our computers instead of using a microphone. If this problem had been solved by Microsoft or any other software company, we would have long ago dispensed with the keystrokes. We would be talking into computers and controlling devices with our voices. But that's not a reality in spite of millions of dollars being thrown at that problem. Now, the other thing that's interesting from the standpoint of language development is this same vowel triangle is used across all languages. So Swedish shoves 16 vowels in this space. And it's really a minefield to look at the productions of Swedish speakers. Japanese does as well, only with 5 vowels, and Spanish with 5 vowels. But they also show, we're as sloppy as we can be. So Japanese speakers will use the whole space and show overlap even in their 5 vowels. They don't make it easier for the kids to acquire by speaking a language that uses fewer vowels. So herein lies the problem. The babies have the ability to hear fine distinctions when you isolate everything in a carefully controlled experiment. But in the real world, they're hearing all this variability and have to, in order to learn words, decide how many categories does my language use and which ones are they. So we've started by studying the babies right from the beginning and saying in studies across many countries in the world, what sounds can they distinguish in the beginning and how does that transition to a set of sounds that are exclusive to a language. So one of the techniques that we pioneered, this in our lab is about 10 years old, looking at event-related potentials, a sort of old technology but very, very improved in studying human cognition now. Babies wear a cap with sensors, electrode sensors in it, picking up the electrical activity as they listen to sound. And in the standard procedure, babies are hearing a background sound like ah, 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 and then on occasion they will hear a different sound like E. And we're looking at brainwave changes between the repeated standard and the deviant sound. And what you see plotted here is the mismatch negativity. Mismatch negativity in adults and babies indicate which sounds the listener is sensitive to. And this technique, and I'll come back to the sensitivity of the brain measure over a behavioral measure a little bit later, but here is the behavioral measure. We've used this one for 30 years. This is a technique that has mom or dad holding the baby. Baby's around 6 months of age. And there's an assistant playing with toys to the baby's right. She has a box of toys and she's bringing them up quietly. These are silent toys. And keeping the baby's attention while the loudspeaker is repeating the background sound. So ah, 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 coming out of this one. And what the baby has to do is, while watching the toys, be attentive to the sound change, because when it changes to anything else, the baby's got 3 seconds to turn their head to the black box. And if they do so at the right time and not the wrong time, the black box is animated and something fun inside lights up. So we run control trials and experimental trials to make sure that control trials, you're not changing the sound, you're still monitoring for head turns, right? Let's look at a baby in this task.
And a baby as young as 6 months old hear the difference between two vowels. This baby is trained to look for the toy when the sound changes. She's being distracted, so she'll turn only when she hears the difference in sounds. The key question, will she turn before the toy lights up?
All right, she's brilliant and she knows it. Okay, so any place on the planet, we're set up in 8 countries to do these tests. With any contrast that's been tested across all those languages, babies show the ability to perform in the head turn task such that they demonstrate their ability to discriminate the sounds. So they need no experience in listening to the sounds. And that's why, as John said, I've called the babies citizens of the world. They're simply come into the world prepared, and that's no trivial task when these acoustic cues are so minute. They come into the world ready for any language. And that distinguishes them from us, right? We're culture-bound listeners, and we are very, very good at the sounds of the languages we've experienced in the first 7 years, not very good at all with the languages that we have not been exposed to. So the critical question is, when do the babies change from citizens of the world to the culture-bound listeners that each of us are? And here the data are very, very interesting. This is data from a study we published in 2006 where we're looking at a contrast that's important for English but not for Japanese. So the ra-la distinction in syllables that codes rake and lake and rod and lod and all of the words that in English are distinguished by R and L but are irrelevant to Japanese. So Japanese speakers produce and perceive R and L as equivalent. We all do that with sounds of other languages. Japanese people will often produce rice for lice, and so we notice it a lot. We're doing the same thing when we listen and try to speak in other languages. So what we see here is that the Japanese and American babies are equivalent at 6 to 8 months of age, and then something dramatic changes in the next 2 months. So this is head turn data. The kids are all above chance, 65%. But then 2 months later, between 8 months and 10 months, something very dramatic happens. So Janet Worker made this discovery that when foreign languages were tested, babies started to fail at about 10 months of age to discriminate that foreign language contrast. And we added this component in 2006, demonstrating that while there is a change in performance on the non-native, there's also a change in performance on the native. Kids are mapping that native contrast. We considered this a very important finding. So we want to know, obviously, what are they doing during that 2 months of time? And the answer is going to be twofold. The answer is that they're doing pretty fancy statistics. There's a computational component to what it is that the kids are doing. And there's also, interestingly, a social component. And the argument I'm going to make in this talk is that the social brain, the social component, is gating or guiding or enabling the computational component. Okay, so I want to unpack that a little bit. Remember in the graph where I showed you there were tons of examples that babies are exposed to in English. The Bill Gates problem is that the variability is huge. So if you look at all instances, the range of sounds we make when we produce the vowel E in English is huge. How is it that infants know and they overlap? If it isn't just the raw occurrence of the sounds, how do they know? And the answer looks to be from studies of statistical learning done by a variety of people, done in my lab, done in Jessica May's lab, at the phonetic level and at the word level by Jen Safran. Babies are literally taking statistics on the input. They're very, very sensitive to statistical structure in the form of distributional frequency with regard to sounds. How frequently, comparatively frequently, are sounds occurring in the language they're hearing, and they end up discriminating the modal values. And when it comes to words, so I won't get back to that today, they're paying attention to transitional probabilities between syllables. So this was a new discovery in the 90s. It was finally an answer to the learning problem. We didn't have a good learning model. We had Skinnerian learning, reinforcement learning. It's totally inadequate with regard to explaining anything about language development. It simply wasn't that we were patting the babies on the back or giving them M&Ms for learning. It had nothing to do with it. So we lacked a learning theory. The statistical learning model provided a way to crack the code statistically. If babies were sensitive to distributional properties, and those distributional properties are there in input, that's a potential leg up. Okay? So the kinds of experiments that were done, the ones I did, were fairly complex. What I was trying to do in these experiments is compare American babies and Swedish babies at 6 months of age with a variety of vowels. The green are English vowel E. The yellow are Swedish vowel, front-rounded vowel U. Okay? And I was trying to mimic that, that set of properties that says there's great variability. How are babies contending with the variability? What we did is use the head turn task to take the prototype. These were adult-defined best instances from the categories. Play that as the background sound. One group of babies in America, in Seattle and in Stockholm, heard the E English prototype. The other half of the kids heard the U prototype. Once they listened to that background sound, we played all the alternative sounds as the, test trials, and to see which ones are the babies turning their heads to. Are they able to organize a category, presumably through statistical learning, their sensitivity to distributional properties? And what we demonstrated in 1992 was indeed by 6 months of age, the babies who've been just laying in a crib or interacting with real people in either Stockholm or Seattle have totally different perceptual systems. By 6 months of age, what we could see is the American infant's response in head turn to the E vowels, the American English E, as opposed to the Swedish U, was totally different. The higher the line, the more generalizability from the prototype to the neighboring vowels. So what the babies were doing is treating more of the E vowels as part of a category, and not so the non-native vowel. Swedish babies, just the opposite. They were organizing their vowels into more of a category when compared to the non-native sound for them. So we had a benchmark finding that's now been followed up by many findings illustrating kids' tendencies, either in short-term laboratory experiments or in 6 months of listening to a language, that the brain is responding to the distributional properties of the language they hear. So it's said to us that this form of statistical learning is important. It's part of what they come with. Now, what I want to develop next is the role that social interaction plays in this statistical learning. So I'm going to develop 2 examples of social phenomena. It's demonstrated in experiments on the way that we, as the input to the babies, right, we're talking to them all the time, what are we doing to shape this process? So let's start with the phenomenon called motherese, or fatherese, or parentees, or caretakerese, whichever one you think is most politically correct. We're all aware of the phenomenon. If you or your spouse or any person in your environment has ever talked to a baby in your presence, you understand that what they do is something kind of strange. They don't sound normal, typical, when they speak to babies. And it looks, again, the physics of the situation looks like this. You bring a mother or a father into the laboratory, and you record adult-directed speech and ID, or infant-directed speech, and you plot the pitch of the voice, you get these wildly different-looking patterns. The mother is talking to another adult, and she says, I had a little bit, and the doctor gave me Bendectin for it. It's not boring. It doesn't sound any different than I do. Average for a female, 300 hertz. It has quite a bit of variation, but it's not what's going on the bottom graph, right? So at the same time, if you're recording her speaking to her baby, she turns to the 2-monther on her lap and she says, hey, can you say ah? Say ah, hey you. Say hi, hi. 700 hertz. It's only 7 o'clock in the morning on the West Coast. It's way too early to get that high. It is really strange sounding. It was discovered by the anthropologists in the 60s who were trekking around to other countries and saying, it sounds really odd when adults talk to children, and particularly to babies. It has a very interesting syntax and a very interesting semantics, but acoustically, it's really a different signal. So you begin to wonder, given that this is a fairly universal phenomenon, what value does this have to the kids? You want to know whether it has value. Also know whether they like it. Do they seek it out? So in laboratory tests, if you give babies in the laboratory at about 15 weeks a choice between motherese and adult-directed speech, and they have to make little head turns. A number of different techniques have been used. Even sucking has been used to turn one or the other on. The kids will do whatever they have to do to turn on motherese or fatherese, no matter what language it's in. Okay, so you give them 20 trials. They'll sample both sides and go for the motherese. So we know that they like it. It attracts their attention. It sustains their attention. Does it do anything for them? We published a study in 1997 looking at mothers across 3 language groups, so English, Russian, and Swedish. And in each case, we were measuring the formant frequencies of the corner vowels, e, ah, and u. Those are the biggest, most different, and most universal vowels in the world's languages. And again, these are the phonetic symbols for e, ah, and u. The red triangles are how we speak to the babies, and the blue triangles are the way we speak to one another. So what you see across all 3 languages is that we exaggerate, we stretch the acoustic cues when we speak to the kids. We also exaggerate facial expression. Instead of saying bead, bid, bood, we say bead, bead. And so we're stretching the differences. I think the significant thing is we're stretching the differences between the critical elements in the language. And we appear to do that no matter what those elements are. So in Mandarin, mothers speaking to their infants will stretch the tone differences. And we've measured other sounds and consonants, and there's an acoustic exaggeration going on that we think is helpful to the kids. And we can, for example, look at these vowel triangles and in individual mothers at 2 months, later measure the 7-monthers' ability in the laboratory to hear distinctions with synthesized, carefully synthesized and different utterances, certainly not their own mothers. And the more exaggerated and pronounced the pattern of motherese was in early development, the better the kids are at 6 and 7 months in discriminating the sounds. So we think it makes a difference to them. We also think it's important that they care about this signal. So one illustration of that is testing children with autism. If you look at toddlers who are diagnosed with autism between about 24 months and 4 years of age, and give them a preference test that allows them to choose either speech or a non-speech analog that mimics the formant frequencies but does not sound like speech, and I'll play it for you in a minute, we get a totally different pattern. The children with autism, hands down, prefer the non-speech, whereas the typical kids will show the opposite pattern. Now here are those signals. Here's the motherese signal. She says, look what I have, it's a pot. And here's the non-speech analog of that. So that's a fairly interesting, strange sounding signal, right? So typical kids will go back and forth, toddlers, they'll listen to it a couple of times, but they certainly don't prefer it. Children with autism prefer it hands down. They'll turn it on over and over and over again. There are 8 samples they're hearing in random distribution. And it correlates very strongly with their symptoms of autism and how severe they are, with the degree of their language deficit and the degree of their cognitive deficit. So we're now using this in tests of siblings of children with autism, where the prediction is that 30% of the children who are siblings of diagnosed children with autism will turn out to be diagnosed with autism within the next 1.5 years. So we're using this test at 6 months to see whether we can predict which of the children will turn out to be diagnosed with autism. So we think of it as a very exciting potential measure. So socially, again, this is a social signal. And what you see with children with autism is really an almost pained look on their faces when you play it. They do not like the intoned. The more melodic it is, which is motherese, the worse they like it. And the more you put a face in front of them close by, the worse they like the exaggeration typical of motherese. They will hide from it by covering their faces. They'll choose whatever else there is as an option, something more mechanical, something either non-speech like this test, but even mechanical sort of robotic speech is more pleasant to a child with autism than a typical intoned motherese speech. So let me tell you a second example where the social role for early language learning is important. This will set it up. This is another graph like the Japanese ra-la finding, Here we're testing babies in Taiwan and babies in Seattle, Taipei and Seattle babies. This is a Mandarin-Chinese contrast that I hear as she. I can't distinguish it. My graduate students and postdocs say, Dr. Kuhl, can't you try a little bit harder? Listen really hard, she. And I'll say, you know, I can't hear that distinction, no matter how hard I try. The babies at 6 months are brilliant at it, equally good in both countries, and then 2 months later, the babies in Taipei are doing beautifully and getting better. The babies in Seattle are getting worse. We decided to do the following experiment. We wanted to learn whether or not a baby exposed to new statistics from a new language for the first time during what we think of as a sensitive period for sound, understanding and mapping out the sounds. What happens if you give them the statistics of a brand new language? They're hearing natural Mandarin for 12 sessions between 9 months and 10 and a half months. Yeah, it was like having Mandarin visitors. A family moves into your house for 6 weeks, and 3 times a week they sit on the floor and play with the babies, right? What's it going to do to their brains at this critical moment when they've now lost the capacity? So they had 12 sessions, 25 minutes each. They heard 4 different talkers, so it really was a pretty natural kind of experiment as opposed to kind of an artificial language. Here's what these sessions look like.
Master, 早安飞。嗨，我们要来讲一个故事哦。今天要讲的故事是《小熊七七探险记》，来看看发生了什么事情哦。小熊七七在这里，好。然后有一天啊，小熊七七说。
Okay, how's your Mandarin coming along? Here's what the babies look like in the session.
绿色的圈圈，绿色的圈圈，转一下，转一圈，嘿，一圈，再一次哦，转一、二、三，2个圈，再一个，1、2、3。
Okay, so what did we want to know? What have we done to their brains with this 12-session intervention? And what's happened to the mothers who are sitting behind them, who have also been privy to 12 sessions of Mandarin, and what's it about? So obviously you have to run a control group of babies, because maybe just coming into the laboratory and being stimulated in this way is interesting to the babies. They love it, and maybe that alone will improve their attention to sound contrast. So we brought another group of 32 babies into the laboratory, and they heard the American graduate students, same books, same toys, same dosage, but listening only to English. So here's the control group. Thank goodness we have an experiment. Listening to English didn't improve their Mandarin skills, and as a scientist, obviously you've got to show that. But look what happened to the babies who had been exposed to 12 sessions of the Mandarin. They're statistically equivalent to the babies in Taiwan who've been listening for an awfully long time, for 10 and a half months. So the message here is you give the right kind of stimulation to infants at the right time in development. They're simply going to map that structure. They can take the statistics on a brand new language. And by the way, the mothers are right here with the control group. It made absolutely no difference to them to have 12 sessions. They seemed also attentive, but their abilities before and after exposure did not change. So this is not something that simply rolls across the basilar membrane and changes perception. It was a striking demonstration of this ability to learn at that point in time. And we couldn't resist, of course, running the following condition. Given that there are tons of DVDs out there on the market and audio tapes that claim to teach your baby Tagalog and French and any number of other languages, the question is, what role does the human being play in this? And because we had all of the results with regard to statistical learning experiments, wouldn't it be the case that if the babies were interested and paid attention to the screen, that the mere presentation of the information would do it? So we brought 32 new babies in and filmed these beautiful DVDs, and the graduate students looking at them said, wow, those are pretty incredible. I mean, they really look convincing, and you can see the face, and you can see the books, and the kids were staring at it. And they looked glued to the machine, to the TV screen. And another group of 32 babies who had their same dosage, audio only. So we projected that the audio-only group might not learn as well, and that the video group would learn perfectly well. But aren't experiments invented for surprise value? Here's the audio-only group. Absolutely no learning whatsoever. Not so much of a surprise, but the surprise came in this one. While the kids had stared intently at the screen, nothing was going on up there. Absolutely nothing, right? So 12 sessions of attentive watching to a flat screen TV and beautiful DVDs did nothing to alter their brains. So again, we had this completely contrasting result. Perfect learning, if you take as perfect the Taiwanese kids who had been exposed for the long time, and absolutely no learning whatsoever, and nothing in between. The audio and video group looked identical and identical to the control group. Nothing going on there. So it made us wonder what is happening here. We've had lots and lots of conjectures. You can begin and end and have 100 possibilities with regard to what's going on. We raised two properties that we thought ought to be looked at first. One is a kind of motivational explanation. Maybe in the presence of other human beings, our arousal is up, our attention is up, and we sort of turn on general learning in a way that doesn't happen when you're not in the presence of another human being. Seems plausible. A second one is different, and that's a more informational explanation. We noted, and you could see in that short video clip, that the babies are tracking nonstop what the adult is doing. They are staring at her and at each new toy that she brings up, trying to follow each and every gaze, and we know that gaze following from a social perspective develops at about this time, and perhaps it's that information gleaned from having tutors label an object while they and the babies are jointly attending to that object. That provides a kind of information that's either totally missing when you're not in a social situation, but reduced over a television set, because while she was looking at her toys, it's not going to be as easy on a television set, and it's not there in the audio condition. So we had the motivation and the informational aspects, and we're following up in experiments now. So here's something that's underway right now, but I don't have the answer to it. What we're doing in experiments now is using a touchscreen technology and asking whether the added attention of babies if you make them turn on the television themselves, you give them control of it for a 10-second presentation, does that increase learning? So the sound isn't good, but watch this baby. She's getting a 10-second exposure to Mandarin, and then she's got to slap the screen to turn it on again. Doesn't matter what she does during the exposure, but when she gets the checkerboard, she has to turn it on again. Okay. Now the kids really like this. Now this baby tries to kiss Lotus on the screen, and they often try to grab the toys from the screen. So there is this sense in which some of the kids don't know whether it's real or not, and they're kind of testing it. So far, with the 20 babies that have been through the routine, we have no effect on the group level, either in the behavioral head-turn tasks or in the ERP brain tasks. They don't appear to be learning it as a group. However, there are some babies, this one in particular, who are highly social and interactive with regard to the television set. Those babies are showing ERP responses. So when they treat this stimulus as potentially social, one of the most predictive variables is whether they talk to the television set. If they vocalize to the TV, they show learning. They can vocalize to their mothers sitting behind them, doesn't make any difference. Vocalizing to your mother, oftentimes the first time they get the hang of turning it on, they'll turn around and go, did you see what I just did? The equivalent in babbling, right? That sort of thing. They're excited about the fact that they made this work. But it's the kids who are talking to the television and trying to kiss the TV or interact with it socially that are showing learning. So we're not done with this, but it's a very interesting thing because it definitely raises arousal and attention on the part of the baby to activate the screen. Here's the other one. Now this is more looking at the informational. We're with Javier Movelin at UCSD in San Diego using his social robot. This is a robot, hunk of metal, that he had sitting in a toddler classroom. And it was just a hunk of metal to begin with, and he was looking at kind of an ethnographic approach. What do the kids do with this hunk of metal? When it didn't behave socially, they would do nothing with it or go hit it. The boys especially, bang at it, do something. but not interact with it socially. As soon as he made the head rotate, so he's got a couple of dots that look like eyes, as soon as the head rotates to follow the kids, there's a camera in the middle of its face, and he added giggling. So as soon as the kids touched it, it would giggle. And when I came onto the experiment, we added Finnish. So this robot now speaks Finnish to the children. Before it hadn't spoken. And when they come by and have a toy in their hand, the robot will ask for the toy in Finnish. And it has a pincer. You can see the pincer arm that will take the toys from the child and put it down a chute. So it becomes a little game where the kids will run over and give an object. And the robot names the object in a Finnish frame, a couple of different sentence frames, and names the object. So we're looking at learning over a 2-week intervention. And the question is, can you learn anything from a disembodied source with regard to language? How social does it have to be? And again, we're seeing huge variation. For the kids who come over and play on short periods of time, there doesn't appear to be any learning. But for the kids who are in sustained interaction with the robot and playing with it, using a lot of toys and staying for a long time with lots of touches and other kinds of smiles and things like that, they appear to be learning. Some of the kids will walk around the rest of the classroom and label everything in sight that they were exposed to in its Finnish equivalent. So these experiments are ongoing, and we're simply trying to crack what the social is about, trying to understand what's happening. We've also started another set of experiments with Spanish, and we've finished our first round, and it's very interesting because we're now looking. The child learning in the social setting is so potent, we're asking, are they learning more than phonemes? So we're now looking at Spanish word learning in the same setting. Are they learning the phonemes? Are they also learning words in Spanish they've been exposed to? So let's take a look at these sessions. We've got 4 cameras pointed at the children and the tutors because the design of the experiment was to say, are the baby's social behaviors predictive of future learning? So we've got 4 cameras, and we're coding micro interaction between the tutor and the baby, particularly with regard to eye gaze patterns, and trying to measure joint visual attention and its degree of prediction for phoneme and word learning. So here are the sessions.
Besito, porque te quiere, ¿no? Con la boca, te da un besito. Qué rico es el pan. Muchas gracias, Lucas. Mira. Todos ustedes. Hola, ¿cómo estás?
Little fatherese there.
¿Te gusta el pan? Qué rico.
Okay, so the same kind of dosage, 12 sessions between 9 and 10 months of age. We have been doing a great number of tests pre and post with 3 hypotheses that we're trying to test. The computational piece says that infants will show phonetic and word learning after natural language exposure at the right time in development. So we expected to see both phoneme learning and word learning, and we've confirmed that hypothesis. They learn words just as well as they learn the phonemes, and you can contrast the words they were exposed to in Spanish from words they weren't exposed to. The social hypothesis says that for both phonemes and words, the more socially engaged the babies are, the more they will learn. We've confirmed that hypothesis. I'll show you a little data for both the phonemes and the words. The cognitive hypothesis is there's a phenomenon out there, and I haven't got time to explain it all, but executive control, particularly inhibitory control, is advanced in bilingual speakers when compared to monolingual speakers. So Bialystok has done a lot of work on adult bilinguals across many different languages, showing not that general intelligence is increased, but this ability to executively control your attention, and particularly inhibitory control tasks. You're better at inventing a new solution to a problem and inhibiting the old solution to a problem when it's not useful if you're a bilingual. And so in the baby tasks, I'll explain them in a minute, but we wondered whether there'd be an association between the kids learning in these tasks over 12 sessions and their cognitive executive control skills. Turns out there is. So here's the social factors work. When you look at joint visual attention between the tutors and the babies and relate their social engagement to their ERP scores, this is the phonetic learning data. You can do this a variety of ways. This is a median split. The best learners are far in advance on the social skills than the poor learners. Here's the scatter plot. You can see that there's the proportion of gaze shifts to get in alignment with the tutor are much higher the higher your peak amplitude of the mismatch negativity is. The data look exactly the same for words and the ERP components for words. So social engagement predicts, during the sessions, predicts the post hoc measure of the brain's response to the phonemes and words of the next language, of the foreign language. Here are the cognitive factor data. So the test we used with the babies is a detour reaching task. So the babies are in a high chair, and we test them before and after. There's a plexiglass box, and there's a toy in the box, and you put different toys in the box and let the babies go through the front door of the plexiglass box to grab the toy, and they'll do this 20 times. Then in their sight, we close the front door and lift the side door, plexiglass slide door, and they've seen it, and they see you put the toy in through the side door. You'd think of it as a pretty easy task to just move your hand movement to take it from the side. Not so. Monolingual and bilingual babies differ on this task. The bilingual kids are faster. They're faster at grabbing through the side door. And what we see in this graph surprised us, that pre-exposure, no difference between the best and poor learners. Post-exposure, the best learners are advanced on the cognitive control, inhibitory control tasks. So there's a linkage. We don't know what direction it goes in, but there's a linkage with just these 12 sessions of experience. So I think that's pretty exciting. So these tests, I think, show you some of the components, the computational components and the social components involved in that 2-month window. I'm not saying it's exclusively happening during that 2 months. It's part of our leg up now on understanding what are the kids doing to alter perception from the universal citizen stage to the other more focused stage of listening in that 2 months. They're doing a computational and a social thing. They can do that for new languages when presented at that time in development. It works for phonemes and for words. One more thing to tout the power of early phonetic learning. If we take brain measures of the kind I showed you before, we're looking at this MMN right here, and you take them at 7.5 months, which is pretty early if we think that they really start changing as a group after 8 months. If you measure them at 7.5 months, we can show now that you can predict the rate of language development to the age of 3 by using a native contrast. And when we first published these data in 2004 using head turn, the critics said, oh, they're just better listeners, right? This isn't to do with language or phonetic perception. And we argued, no, the prediction is not the same for a non-native contrast. The argument is that native contrast, locking on to those early, will propel you to advance in language very strongly. Your ability to discriminate the non-native contrast at 7.5 months means you're still in stage 1. You're still in phase 1 of development, where all phonetic contrasts are equally interesting. So if you're still good at 7.5 months at the non-native, you're going to develop more slowly. And the data bear this out. So here's a baby wearing the cap. This baby's native response at 7.5 months, huge negativity. Here's the non-native response at 7.5 months. This baby is already showing the pattern that most kids will take till 10 months to show. And here's the curve for the entire group of babies, word learning at 14, 18, 22, and 26 months, out to 30 months actually. The native predictor, the top half of the distribution, the bottom half of the distribution. It really helps to be good at native phoneme discrimination. The non-native predictor, these two curves are reversed. You're better at word learning if you're poorer at non-native, in the sense. And these are both, on growth curve modeling, these are both statistically significant. So it entails this sort of mapping, this neural commitment, which starts the process, in my view. The kids begin to commit to the sounds of the native language and, in a sense, give up. Not that they can't discriminate it anymore, but they're not attending to it anymore. There is still, at the group level, an ability to hear that distinction, but they're inhibiting it. They're attending to the native language. They will zoom forward. The kids who are still attending to them equally are going to be slower to develop language. Okay, we're running a little short here. I have another brain finding, but I think I won't say much about it. If you do fMRI tasks at 5 years of age and you measure children's language, IQ, and social skills and the SES of their families, the most powerful predictor after false discovery correction for multiple comparisons is the socioeconomic status of the children's families. Broca's area, measured in an fMRI machine, shows much less specialization, left versus right hemisphere. The poorer, and we're not actually measuring income, but it correlates with income. We're doing the Hollingshead, which is a standardized measure of the family's socioeconomic status. What it's really measuring, both parents' education, both parents' occupation. And what we're attributing this to, you see this dramatic correlation for SES correlating with Broca's area. I mean, what it means is that at 5, it's not an equal playing field. These kids have equal IQs. These kids have no deficits that we can measure. This is just the middle of the scale. It runs from 0 to 66. We have nobody below 30. These kids all have parents who have high school degrees and are employed. What it says is the richness of that environment affects the development of certain brain structures. And in this case, we were tapping the brain structures during a rhyming task in Broca's area. Follow-up tests using structural MRI say that the complexity of the language these kids hear is systematically lower, syntactic complexity systematically lower, the lower the SES. So in families with lower SES, what they talk about is different, and the complexity of the language is different. They don't use mental state verbs to talk about what are people thinking? Why did they do that? You know, what was going on in their minds? That kind of complexity is much reduced. The language is more a directive. Do this, don't do that. There's simpler structures. It makes a difference what's going in. And so I think these results are very, very exciting. But here's really where we're going. We've been using ERP for a decade. We'll use fMRI with the kids over 5, but we really want to measure. We can start with the newborns, go all the way to the aging senior, and understand what's happening with the brain and social stimulation during language. To do that, we need a brain imaging technique that uses whole brain processing and allows us to look at social systems, language systems at the same time. So we have to get beyond molecular neuroscience, which focuses at the individual level, at the biochemistry. Very, very important, but it's not systems neuroscience. Systems neuroscience wants to look at whole systems, memory, executive function, language, and understand it. So we're buying this machine. We open May 24th, a couple of months from now. This is a magnetoencephalography machine. Looks like a hairdryer. It is non-invasive, totally safe, noiseless. It measures with 306 sensors the activity, the magnetic fields produced when millions of neurons work together. And so you're picking up with these 306 sensors the magnetic fields that occur at the neuronal level. This is directly mapping neuronal signals. And of course, it's an engineer's physicist's dream because it plots with millisecond and millimeter accuracy where the brain activity is during cognitive tasks. So we're excited about this mostly because the babies can be put in the machine. So we're the first in the world to record babies doing a cognitive task. This is Emma in Helsinki, where we had to do the measurements before we got our own machine. She's listening through insert earphones to the sounds of many languages, and you can see she can move. We're tracking her head movements with this little cap that's correcting we are correcting now every 100 milliseconds for where the location of her head is in the helmet. So we want to know where Broca's area and structures are at all points in time. So we're very excited about this, and illustrated in our first finding in 2006 how powerful it's going to be. This is basically a feasibility study, but we had newborns in the machine measuring auditory areas, superior temporal and inferior frontal, Broca's area, in the newborn period at 6 months and at 12 months, during speech and non-speech. So what we saw in newborns is that there was no activation in Broca's. Obviously, superior temporal auditory areas respond to speech, non-speech, everything equivalently. But when you look just at the speech, newborns by 6 months you can see simultaneous activity in these two areas of the brain post-syllables, and you don't see this for non-speech, and by 12 months it's even more active. It's as though Broca's area is recognizing or attempting to simulate. We don't know exactly what it is. Mirror neurons would project, but that work's been over-interpreted. In humans, these shared neural systems exist for perception and production. We're trying to understand how they might develop. When does Broca's area know that that's speech? What's it doing to try to emulate that movement? So these are the kinds of experiments we're going to be able to do across the lifespan with MEG technology. So in conclusion, we can say a lot more about early language development than we could before. The studies done all across the world are demonstrating important things about learning skills that we didn't know that kids had just 2 decades ago. We discovered this computational ability of babies that's implicit and happening all the time. And now we can say that that's sort of controlled a bit, we believe, by the social brain. Social interaction has something to do with turning on this computational skill. At least we think so. And we think that could be helpful in evolution, that we're not constantly gathering statistics on things that don't matter. With language, it matters that it's a human talking to you as opposed to the sounds coming out of something irrelevant. Bilingualism may affect cognition. It certainly does in adulthood. We're interested in the babies. We've got some suggestive evidence. We believe that motherese assists learning, and others have said it before. We're trying to understand in the early period, what does it do at the phonetic level to assist? And maybe the more important thing to underscore here is an interest in language helps children learn. And if they don't have an interest in language, as is true in children with autism, that learning is impaired. We think of phonetic learning now as a pathway to language. The early language environment is extremely important. The kids get talked to. The stretching we do in motherese, but that locking on, that initial learning of which sounds am I supposed to pay attention to and which ones am I allowed to ignore, that propels you forward. That scaffolds you towards more complex levels. The critical period phenomenon we think is affected by experience, not time. I didn't present you all the data that we have. The hypothesis is that you're neurally committing to the structure you hear early in this combination of social and computational learning. It's mapping structure in the brain. And that structure in the brain becomes your default value for language. That's why you can process language at 0 to signal to noise ratio, and you're so adept at adjusting to the variations that you hear. We think that it isn't going to be time per se. It isn't the maturational hypothesis of Lenneberg. It's more about learning, and that lends itself to very interesting experiments. And then finally, these new neuroscience tools, particularly MEG, we think is just going to change the world as we know it, as we uncover more surprises about how kids go about this marvelous task of learning a language. So in closing, I just want to recognize, it takes an army to do research, right? I want to thank all the students and the people across the world who have contributed to these studies. There are tons of them. The interdisciplinary and the kind of international team that we've pulled together is really powerful in doing this kind of work. You simply can't do it in one laboratory by yourself. You can't just use a single language. It also takes an army's worth of money, right, to conduct these experiments, and so we all recognize how hard it is to procure the grants. I think language is a very strong interest to people. Cognition development is a very hot topic, and I think we can all do well to mine society and the grant agency's interest in developmental cognitive neuroscience as we kind of move forward. I think it's going to be a very exciting decade. So thanks for your attention, and we'll take some questions.
So just a couple of announcements before we take questions here. One is that if you have a question, you should use a mic. There will be people walking around with microphones. I'll stand in front of this microphone here to help right now. Because this is being recorded, we'd like you to use microphone. The other announcement is that we're doing something different this year. We're having, if you're an undergraduate and would like to talk with Dr. Kuhl later on this afternoon, we're having a discussion session over at the Institute for Research in Cognitive Science. Anybody who is an undergraduate who's interested in this, you're welcome to attend. It's at 3401 Walnut Street on the 4th floor, and it's at, I believe, 3 p.m. 3 p.m. So please come if you can. And then finally, there is going to be a short reception outside here as well after the question period. So I'll let you take the questions.
Lila
And the microphone
is coming.
I want to go back to the first part of your talk,
Yeah.
Where you introduced the problem that the discovery of the phonemic system is made difficult or is made impossible in its own terms by the enormous variability and overlap.
Mm-hmm.
Okay?
Right.
And yet the mystery is going to be that somehow or other children solve this problem.
Right.
Right? So the problem seems to be unsolvable in its own terms. As we know from Bill Gates, a very smart guy, and his 500 cohorts, and they're working, and people have been working on this for 50 years,
right.
As we know, the problem seems unsolvable. And it seems unsolvable for the usual Platonic reason, because of the overlap, you don't know which items belong in the set.
Right.
Right? Which are the
Correct.
E's.
Right.
So I was interested in your first experiment, very early experiment, in which you gave infants a prototype.
Right.
So here's the central member. And given the central member, well, then they can do statistical learning.
Right.
But we're faced with the problem here that in natural running speech, the children aren't given the central member.
Right.
Right? So, now turning to the second half of your talk, you turn now to the social question.
Right.
Okay, and as I saw in especially the Spanish guy with the little kids.
Yeah.
Okay, it seems to me that you see something much more specific than saying, well, here was the computational and here is the social. But more specifically, social at its margins, you have to get them interested. But that's just an enabling condition. So I want to try this on you.
Yeah.
The causal condition is the following. You have to solve this problem top-down to solve the Plato problem,
Right.
right, which are in the system. So you have to know which count as the E's,
Right.
right? Or you can't solve the problem, just too much variability, right? But you can solve it if it's peekaboo. It's always the same object.
Right.
So if you're socially interested in the problem, that enables, but that problem's computational too. It means
is.
you have to solve it top down.
Right. Yeah.
So what do you think of that?
I think those are wonderful questions. So let's go to the first one first about the prototypes. So where do prototypes come from? I mean, okay, so are they Platonic? Well, one answer was they're Platonic ideals. They're built in, and we say no. You know, they're derived statistically through a process that we don't quite understand, but they're derived from statistical distributions. Maybe it's that's one possibility, but computers aren't solving it that way, right? So the second one, which comes from the social piece, is to say that it's actually mediated through words. That knowing that something is referred to by different people in the same way allows you to decide, okay, everything that is referred to in the same way must be part of that statistical distribution. However, you know, it's hard to imagine that the kids at 6 months, so the data show that by 6 months the babies in Stockholm and the United States are solving it already. So either they're cracking the word code much earlier than we think they are, possible, or there's something else going on that we don't quite understand. Yeah, oh yes, yeah. You may only need a few words. Yeah, you may only need a few words. And, you know, the Mother East phenomenon does do this in spades by not only naming objects in the presence of kids and providing more prototypical examples, right? Much more prototypical in Mother East, as we saw from the stretched triangles, but also varying. They do two things. They develop a more prototypical average but they also have greater extent of variation. It's almost as though motherese tries to be multiple talkers. So it's possible that's a leg up on the solution, which would explain why do computers not do it? Why isn't it just statistical? What's the piece of the social, the word, maybe the vehicle in? The Spanish experiment's interesting because we measured both words and phoneme learning at the same time. Kids are exposed to Spanish, 12 sessions. Post-session, we measure both phonemes and words. We ask the question, at the individual level, do all kids show one of the two first? So some kids may learn one and not the other, show learning of one, not the other, and some may show learning of both. The kids who learn both or neither are not as interesting as the kids who show learning of one and not the other. Interestingly, we see it almost, we're not done with this analysis, it's not, so don't hold me to this. Kids seem to do it differently. Some kids are showing phoneme learning, not word learning yet. Other kids are showing word learning, not phoneme learning yet, suggesting that different kids may go at this differently, which would be very interesting. But we have to do more analyses. We probably have to do more experiments to understand exactly what they are. But you're absolutely right. They've got this problem. They've got a big problem. Variation all over the place. Social mediation to help steer them in the right direction. Great computational skills, but you still have to know over what to compute. How do I compute? So categorical perception will help them somewhat, right? Because they are hearing these boundaries. So they've got some gross partitioning that would say, gather the statistics on this acoustic part of the map, put them all together. So it could be something sloppy like that until they hone it to objects. We don't know. Give us some business for a while, right? Go ahead.
So you said that autistic kids prefer robotic sounds.
Yeah.
Is it because it's just disturbing to them? Or can robotic language actually help them learn language better?
Well, it may be both of those two. So on the one hand, what we see is behavior that looks like they're afraid of the face and the voice. They will never choose the face when they have a choice. So they cover their eyes if we don't give them a choice. And they also, if you give them a listening choice, they will steer clear. The more emotive the signal sounds, the less they like it. So I think, MEG data, again, what's happening to the amygdala when they hear faces, when they see faces that are very animated as opposed to an object, they always prefer objects. So it's possible that fear centers in the brain will illustrate some oddity of their brain's processing of signals. Somehow what typical babies find pleasurable, speech is the hands-down choice of children given a choice, and faces, most interesting visual stimulus, that's different in children with autism. And I think that could prevent their learning. The second question is, what if you presented speech to children with autism through the robot, with a robotic voice? We haven't tried it yet, but I think it's extremely interesting to think about that. It might help this initial mapping process.
Thanks.
Yeah. And we'll come back over here.
Hi. I wanted to stick up for the machines a little bit.
Okay.
That
Go for it.
scatterplot that you showed of English vowels, which I think was published in your 2004 Nature Reviews Neuroscience article, came originally from Hillenbrand, 1997.
Right.
And they did...
And earlier from...
did...
Peterson and Barney.
Well, they replicated Peterson and Barney, but they did discriminant analysis on the measurements for those vowels, and they got 97% correct. Vowel identification, 92 to 97, depending on exactly how they set it up. So, in fact, that plot showed F1 and F2. They threw in F0 and duration.
Right, which was helpful.
Which is helpful because humans also get that.
Right.
So I'm not trying to suggest that the speech recognition problem by machines has been solved, but I think you radically exaggerated how far away the machines now
that's
are.
Fair. Yeah,
also,
that's fair.
You also said that speech recognition requires words to be separated, and that actually hasn't been true for quite a long time. it certainly doesn't get perfect transcription, and there's certainly plenty of research to be done in that area. But I think there might actually be an opportunity for greater confluence of research interests and results from the results that the engineers
No,
are
I'm
getting,
excited about
and from your research as well.
Okay, thanks for making that clarification. I'm excited about the engineering perspective and think that greater experimental sharing between human learning systems and machine learning systems is really important. So a postdoc of mine, DeBoer, and I actually looked at machine learning for motherese and adult-directed speech and could see the value of motherese signals and that kind of thing, especially with regard to the robustness after training to new data sets. So I think there has been a lot of progress. I think the progress may not be happening so much at the phonetic level. And I was only trying to illustrate with that diagram from Peterson and Barney. I mean, what my understanding is, we have not got the ability to play natural language into a machine learning system and have it derive the categories of the language. I mean, that's the ultimate test of whether or not the machine can process natural language in a way that allows it to sort. So when speakers like in the Hillenbrand or Peterson and Barney are producing he'd, hid, had, who'd, highly constrained, CVC, prototypical examples, that's not really a fair test that compares them to the babies. So but I do think that the motherese productions, not the kind of stylistic stuff we do when we are trying to be made understood by a machine. So sometimes when machine learning algorithms make a person repeat, they do just the wrong stuff, right? They do something that's not what we do when we pronounce these clear instances of motherese. I think there's a lot to be learned by using input into machines that really constrain the syntax, constrain the vocabulary, and enhance the acoustics in the way that motherese does. So I think that it will be a very promising line of studies. And if we ever get to the place where robots are capable of teaching foreign languages to kids, I think, again, the engineering psychology links will be stronger still to try to understand what kinds of learning can we do from machines, what kinds of learning can machines do and humans do that are comparable or not. That remains an interesting question. I used to tell Bill Gates that his computers needed a life and a brain, but I've modulated that a little bit over the years.
I'd just like to comment on your work with the autism. Conventionally, it's difficult to diagnose an autistic child until they're about 18 months or so. And yet there's another test that works completely in agreement with your findings. If you project on a screen the picture of the mother, the autistic kids will look at the eyes. Mm-hmm. The normal ones will look at the mouth. Yes. And that seems to mesh very well with your findings.
So Ami Klin's data.
Yeah.
Yeah, I think that's really interesting. And from the standpoint of the clinicians as well as the scientists, the earlier that you could diagnose these children and the earlier you could attempt treatments that are getting at what you think the fundamental cause is, the better we would be both scientifically and from a clinical standpoint. I think it's fascinating. I think these early precursors, the eye gaze, the social work that Clint's doing, and this auditory, this sort of early language precursors in the auditory domain have real promise. Again, tapping the social and the linguistic preparation for language. Yeah. Thank you. Other comments? Yeah.
Just a specific question about for the children who were exposed to Mandarin Chinese between they were 8 to 10 months. So have you studied them after they became older, for example? Like, do they keep the ability or do they lose it?
Well, we're really interested in the forgetting function for adults and children, thinking that it's quite different. That children, as we saw in these slides, learn so very well, and we think that it has some staying power, but not forever. So we brought the kids back in at 14 months, and we could see the ERP signatures of that learning are still there. That's quite a few months after, without any intervening Mandarin experience. But then by 18 months, it's gone. So we don't see the neural signature anymore. The hypothesis would be, but we couldn't do that with these kids, if you brought them back at 3 or at 5, that they would look different when exposed again to Mandarin than the kids would who, if they had never been exposed, like the control group. We didn't have enough of these children we could bring back in, but we'd love to do experiments where we demonstrate that there is some staying power. This early experience that you have really has a kind of potency with regard to the neural structure, and the vestiges of that would remain quite a long time. Whereas in adults, we know that when we're exposed to foreign languages, we can sometimes learn, but it doesn't stay. So there's something different about the short-term memory system and long-term memory systems for language and speech that's going to link to the critical period that protects us from being written over, right? When you go to Japan for 2 months, it wouldn't be good if your English skills were written over by your newly forming Japanese skills. So there's something about memory systems and the critical period that we'd like to understand, and maybe the tractable experiment are these forgetting functions after interventions to see, what's happening. And of course, brain imaging with that would tell us something about what's happening in the auditory areas, in Broca's, and in executive function areas.
Okay, thank you.
Yep.
Well, there's a phenomenon that's been quite important in my own work, which is quite puzzling, but all linguists are familiar with it. Children, there's massive evidence to indicate that children do not acquire the foreign accent of their parents.
Yes.
And this happens quite late, at a period that seems to be considerably later than the intensive
really
learning
early
program.
stuff.
So I was wondering if that later ability can be modified by social factors of a sort that we don't yet understand.
I totally agree with that. I think that we may see that the social factors are so potent that when you take, we've been looking at toddlers who come into the country, say from Japan or from Taiwan, speaking either Mandarin, their families have spoken Mandarin or Japanese. The parents are not good English speakers, and so they are attempting a little bit of English at home, but basically it's the children are exposed to one language at home and a different language in preschool. And what we see is as soon as they develop, this is mostly anecdotal, ethnographic kinds of research, that as soon as they develop a social group, a group of pals, a group of friends, the 3-year-olds, 4-year-olds, that they completely lock on to the language style of their peers. So I interpret that as a social effect, that we don't have it made tractable. I'm more interested in teenagers who are, edging towards the end of the critical period, and there's also there a potency with regard to social factors and a group of emotionally close kids and a mimicry, this is in speech production data, a mimicry of the kids in their social group. So I think the social factors are really strong. The question is, why aren't they strong for adults? Why don't social factors, or do we avoid social factors? As adults, we protect ourselves socially by we don't move to foreign countries and develop close friends to the same degree as kids would do when they're kind of desperate for that contact. What is it about the social that might change over time if this is a real fundamental explanation to what's going on with learning mechanisms? So I think that's a puzzle. But it's absolutely true for the kids that this peer group will win out over the parents hands down. Very potent. John.
So this is somewhat related to that. I think a really, I don't know the developmental literature well enough to say this for sure, but it seems like an understudied topic in this area is the adaptation to particular speakers, adapting to speaker variability. It would seem, especially for these computational problems, that one of the things that the child has to learn is, is a model of an individual speaker? How quickly can you develop a model of the properties of this individual speaker, and how do these map onto the so-called invariants? Or maybe that's what the invariants are, developing a model for each speaker quickly. So I guess part of the question is, are there studies of that sort going on? How early can infants adapt to different speakers? And also, would this be part of the puzzle that a crucial piece of the puzzle that's being overlooked right now?
I don't think the right kinds of experiments are going on, and these are the ones where the engineering approach would be very interesting to compare to infants. So what you'd want to do is model learning with machines and with infants if you could control the kinds of speaker variability that they're exposed to. So on a completely statistical explanation, you'd imagine that kids are attempting to develop the distribution of allowable instances of a particular type. Now you have to decide what you're averaging over, but let's say that you can limit the extent to which there are speaker variances in the input of a child. Maybe a child raised only by the mother for the first 6 months, just to do a thought experiment, right? So you'd be overrepresenting in your statistical distributions her utterances. They would simply look like her. And so when other females, males, and children come into the picture, that statistical distribution has to be modified until the very next instance you hear doesn't change the distribution anymore. So once you've heard, 1 million instances of a vowel, and you've heard many different talkers of different ages, is that the point at which you stabilize your distribution? Doesn't change anymore because the next instance is not new. It's subsumed by the distribution. So how that happens, the stability and how many instances does it take, we have absolutely no idea how much it takes. And then we also know that we drift both in speech production and in speech perception. If you go to Britain, you will drift your categories. You'll sound more British with regard to your productions. You'll also perceive things differently. So why is it that you don't overthrow your distributions when you're trying to learn a foreign language, and you're not completely mapping a whole new structure when you go to Japan for 2 months, yet you can drift when you go to another country? You begin to sound different, and your perception is shifting if you do micro perceptual tests. So how does the neurobiology protect us from the overthrow problem while still allowing us to adjust, again, socially? Why would we do it? Well, because socially it's sort of interesting to adjust to the behavior patterns, the speech patterns, the listening patterns of the social group you're in. Comparing human learning experiments with machine modeling experiments that look to see what does it take to stabilize a distribution, think of it just statistically. That's an interesting problem. And I've been thinking about it, and I write about it, but only as a, Duncan, it's not something I'm solving in experiments yet. It would be nice to design those and conduct those. I think that's a really interesting question, but I don't know how that works. We have a degree of openness, but we're not completely open. How is that?
Well, if that's all the questions, thank you very much.
Yeah, thanks. That was great.